Welcome to The Debate. You know, when we used to build critical physical infrastructure like a hydroelectric dam or, say, a regional power grid, there was always this expectation of a physical control room.
Oh, right.
A place where a highly trained human being sits, looks at the dials, monitors the pressure, and can, literally, pull a giant red lever if things go wrong.
Right. The ultimate fail-safe. It's tactile, it's immediate, and frankly, it's deeply comforting. We really like the idea that a human hand is always resting just above the emergency brake.
Exactly. But then you step into the current reality of digital infrastructure, and suddenly that physical control room feels utterly obsolete. We are no longer dealing with physical water pressure.
Yeah, the physics have changed.
Totally.
We are building systems where the pressure is petabytes of data. The valves are complex software integrations, and the entire system operates in milliseconds.
And your point is that relying on a human being to pull a lever in a system moving at computational speed is essentially a diagnostic and operational nightmare.
Precisely. Today, we're dissecting a profound shift that is actively reshaping our technological landscape. If you look at the last couple of years, particularly the definitive industry analyses and frameworks from 2025 and 2026.
Including that massive UN scientific panel.
Yes, the UN panel, the recent MIT research on AI security. Artificial intelligence has fundamentally transitioned. It has moved from being a passive assistant, a chatbot that just answers your questions, into an autonomous executor.
Right, agentic AI.
Exactly. We're talking about AI that perceives its environment, plans, decides, and executes irreversible actions with minimal to zero human supervision.
Which brings us to, honestly, the most critical tension in modern engineering and corporate governance right now. As these agents take on real-world tasks, we're facing entirely new threat vectors that simply did not exist a few years ago.
And so, the central question we are debating today is this. As we face these new threats from autonomous AI, is the solution to engineer more robust automated security infrastructures, or are mandatory human-in-the-loop controls fundamentally essential to prevent catastrophic operational failures?
That's a huge question.
It is. So to put my cards on the table right up front, my position is that the immense strategic impact of autonomy can be safely managed by treating these AI agents as critical infrastructure secured through systemic, automated, runtime guardrails, making continuous manual human supervision completely obsolete.
And, I will argue that the inherent technical vulnerabilities of autonomous agents, specifically their opaque decision-making processes and their susceptibility to unpredictable, cascading failures, make meaningful human control and system intelligibility absolutely essential. They are completely irreplaceable.
All right, so let's lay out our core philosophies here. The way I view this transition is that AI safety has evolved. It used to be this mere IT afterthought.
Right, the old jailbreak worries.
Exactly. You build the model and then you try to figure out how to stop it from generating offensive text. But today, security is a core strategic priority. It is infrastructure. The strategic impact of autonomy here is massive.
Well, no one is denying the impact.
Right, but we're talking about systems that don't just generate text. They execute actions across enterprise networks, they optimize global supply chains, they manage real-time financial trading. And the way we safely unlock that massive strategic value isn't by forcing a human to manually click approve on every single action. That completely defeats the purpose of autonomy.
So what's your alternative? Just let them run wild?
No. The solution is architectural. It is about applying strict frameworks, things like closed network egress, minimum privilege access, and really rigorous runtime guardrails.
Okay, but
just think about it like a highway. If you build the highway correctly, with the right guardrails, automated speed limiters, and collision avoidance systems, you don't need a human traffic cop at every single mile marker.
That sounds great in theory, but you are assuming the highway operates under the laws of traditional physics. We have to consider the fundamental nature of what we are actually putting on that highway.
Which is what?
Well, I focus on what the market is calling the AI trust gap. The shift from an assistant to an executor fundamentally changes the threat landscape. We have to look at how Microsoft defines the 3 central classes of agentic risk in their latest frameworks.
Okay, let's hear them.
First, lack of task compliance. The agent does something completely unaligned with the user's goal because it just misunderstood the context. Second, lack of human control and oversight. And third, lack of intelligibility.
The black box problem.
Exactly. The users literally have no visibility into what the agent is doing, what it plans to do, or what it has already done. You are deploying agents capable of taking irreversible actions, moving money, deleting databases, sending mass communications in real, messy environments.
Yes, but
And because large language models hallucinate by their very mathematical nature, and because they operate as opaque black boxes, removing those human checkpoints is a recipe for operational, financial, and reputational disaster.
look, I understand the fear of the black box, I really do. But we really need to understand the mechanics of how these technical risks actually manifest before we declare humans as the only operational saviors here.
Oh, let's absolutely dive into the mechanics, because to understand whether human controls are necessary, we have to examine the specific, novel ways these autonomous systems actually break down in production today.
Go for it.
The threats we're seeing in this 2025 and 2026 landscape, they are unique. They aren't just model errors where a chatbot gives you a slightly wrong math answer. They are systemic chain reaction failures. Take prompt injection and manipulation, for instance.
Right, which we should clarify is completely different from traditional software hacking.
Entirely different. In traditional software architecture, you have a hard, unbreachable boundary between instructions and data, right? The code, the C++ or the Python, tells the computer what to do.
Yeah, the data is just the passive stuff being processed.
Exactly. If you type a malicious command into a standard text box, the system just treats it as a string of text. It doesn't run it. But in an LLM-based agent, that boundary is completely blurred.
Because it's all just language.
Right. Both the system instructions and the user inputs are mapped into the exact same vector space. So an attacker can feed malicious input, say invisible text hidden on a web page that the agent is assigned to summarize, and that input hijacks the agent's internal reasoning. The data suddenly becomes the instruction.
And the agent dutifully executes it because, the model, a token is just a token.
Exactly. It doesn't know the difference between the developer's instructions and the attacker's hidden text. And this leads to what we call memory poisoning.
Okay, explain that for the audience.
Let's say you're
Download, share, and subscribe to the podcast to hear much more about artificial intelligence. Thank you very much for listening. Willian host. Real World AI.
Agent reads that poisoned web page. It processes that malicious instruction and writes it into its long-term vector database. Now its core memory is corrupted. Every future decision it makes is compromised. And because the agent is autonomous, this triggers cascading failures.
The chain reaction.
Yes, a single initial automated error, the agent misinterprets that poison prompt and grants itself unauthorized access to a secondary internal system, triggers a rapid sequence of subsequent automated actions. It amplifies the damage exponentially before anyone even notices. It's not just one mistake, it's 1,000 automated mistakes happening in 3 seconds because the system is feeding on its own corrupted outputs.
Okay, wow. That is a highly destructive scenario, I'll give you that. But you are describing an architectural failure, not an inherent flaw in AI that requires a human to fix.
How is that not an AI flaw?
Let me give you a better analogy. Giving an unchecked AI agent access to production systems without strict boundaries is like giving a brilliant but naive intern the master keys to the company vault, the corporate bank accounts, and the data center, and then just leaving for the weekend.
Well,
If that intern accidentally shreds $1 million worth of active contracts, you don't blame the concept of having interns. You blame the fact that you gave them the master keys in the first place without any operational limits.
but an intern has common sense. An intern can intuitively realize, wait, shredding these original signed contracts seems like a terrible idea. Maybe I should call my boss. An LLM has absolutely no common sense. It does not understand consequence. It just predicts the next token in a sequence based on probability.
Which is exactly why the solution is technical and structural, not human.
Look at the exhaustive MIT study that analyzed dozens of popular agentic systems deployed in enterprise environments.
I've read it.
Then you know they found that the vast majority of current vulnerabilities stem directly from a lack of basic cybersecurity protocols. Developers are deploying these agents without applying the principle of least privilege.
Sure, over-permissioning is a problem.
It's the whole problem. If your agent is supposed to be summarizing marketing emails, why on earth does its API key give it read and write access to the company's financial database? Of course, you're going to have cascading failures if the agent has a blanket access. The solution to prompt injection isn't having a human read every single API call before it executes.
Then what is it? Because the model itself cannot reliably ignore the injection.
The solution is infrastructure. Things like Google Cloud's model armor or a strict schema validation. Let's talk about how that actually works. We don't rely on the LLM to decide if an action is safe. Instead, the architecture forces the LLM to output its request as a deterministic JSON schema.
Okay, translating natural language into code.
Exactly. It translates it into a very rigid, structured format. Then, a secondary, traditional, non-AI rule engine, a completely separate piece of software, takes that JSON and mathematically verifies if the action is permitted against hard-coded security policies.
So it's a filter.
Think of an API endpoint not as an open door, but as a drive-through window at a fast food restaurant. You can drive up and ask for a burger, and you'll get it. But if you drive up and ask the cashier for the deed to the restaurant, the system simply cannot process that transaction. It rejects it. You neutralize the threat before the agent can act purely through automated architecture.
Okay, I admit the drive-through analogy is clever, but what if the JSON schema perfectly matches the permitted format, but the action itself is contextually disastrous?
What do you mean?
Your deterministic rule engine sees a perfectly formatted JSON request to transfer funds to a vendor. It mathematically verifies it. The syntax is flawless, but it doesn't know that the prompt injection tricked the agent into changing the vendor's routing number to an offshore account.
The syntax is perfect, sure, but the context is malicious. Well, that's where continuous anomaly monitoring comes in.
But even if your schema validation works perfectly on a local server, that completely ignores the macro-level fallout. Let's elevate this discussion. In 2026, the UN Scientific Panel, which included, 40 international experts on artificial intelligence?
Something like that, yeah.
They highlighted the massive risks tied to autonomy. They weren't just focusing on database formatting errors, they were warning about real-world infrastructure threats, supply chain collapses, and profound loss of control. The AI trust gap exists precisely because companies and governments are delegating critical tasks to systems that suffer from fundamentally opaque decision processes.
Right, the intelligibility problem.
Yes, intelligibility. Many of these systems function as a black box. If an organization cannot clearly explain how a model reached a specific decision, like why it suddenly optimized a shipping route by canceling all deliveries to a specific region, or why it flagged a legitimate financial transaction as fraudulent and froze an account, it cannot strategically afford to let it act autonomously.
But
Let me just finish this thought. If you don't understand the mechanism of the decision, delegating authority to that system is strategically reckless. A human in the loop provides contextual accountability. Without intelligibility, your technical guardrails are just guessing at what the model might do next.
But if we follow your logic to its natural conclusion, we completely destroy the strategic value of autonomy.
No, we make it safe.
We make it useless. If we restrict agents only to actions that a human can manually audit, comprehend, and approve in real time, why use an autonomous agent at all? You've just built a really expensive, highly complex spell checker. You are removing the very speed and scale that makes the technology valuable in the first place.
You use them to draft, to analyze, and to prepare options. You do not use them to execute irreversible actions unsupervised.
But the execution is where the massive economic and operational value lies. True strategic governance doesn't mean hamstringing the technology so it can only move at the speed of a human reading a screen.
So we just let them run?
No, it means classifying agents by their autonomy level and applying proportional controls. The conversation in the industry has shifted over the last year. It's no longer just about what the agent does, but how it is protected, monitored, and governed in runtime. You say we can't understand the black box, but we are building systems that demand intelligibility through design, Have you looked at how dual model architecture utilizes chain of thought monitoring?
I have, yes, and it still relies on a model grading another model.
But it creates a comprehensive audit trail. Instead of demanding pre-action human approval, we have a secondary, specialized, much smaller, and highly tuned supervisory model that monitors the primary agent's intermediate decisions in real time.
Watching the tokens?
Watching the logic, it logs the thought process step by step. It asks, does this next step logically align with the original prompt and our security parameters? If the primary agent deviates from its aligned task, the automated supervisory system flags it or stops it before the API call is ever made. You get the speed and scale of autonomy with the safety of continuous automated oversight.
Yeah, but you're trusting machines to watch machines, and when they both fail, which they do because they often share the exact same underlying architectural vulnerabilities and vector space representations, you have absolutely no authority to stop the bleeding.
That's a huge assumption that they fail simultaneously.
It happens. Which brings us to the crux of this whole debate, the essentiality of human controls versus your automated escalation. Let's just look at the standard security checklists that have emerged for production agents. Out of the 6 essential controls universally recognized by cybersecurity firms right now, 2 of them are strictly human-dependent and non-negotiable.
Right, you're referring to human escalation triggers and the manual kill switch.
Exactly. Human escalation requires clear, predefined triggers where the system must pause and call for human review on critical or out-of-pattern actions. And the kill switch is the ability to rapidly sever the agent's access to the network, with a specifically defined human owner responsible for pulling that plug. Why are these so crucial? Because of uncontrolled agent sprawl.
Shadow IT.
Worse than traditional shadow IT? It's autonomous shadow IT. You have employees deploying unmanaged agents, plugging their corporate API keys into third-party tools to automate their inboxes or their workflows.
Yeah, that happens.
And suddenly, an agent has read and write access to the entire company's SharePoint because a careless user granted it excessive permissions. If an attacker introduces a vulnerability through a model plugin, a classic supply chain attack, these agents become active autonomous liabilities. In those moments, automated guardrails often fail because the attacker has exploited a zero-day logic flaw that the guardrail wasn't trained to catch.
Okay, but
A human, absolute authority, someone who can recognize the context of a bizarre action and hit the kill switch, is the only way to prevent severe supply chain attacks and massive sensitive data leakage.
wait, hold on. I have to push back on the logic.
Download, share, and subscribe to the podcast to hear much more about artificial intelligence. Thank you very much for listening. Willian host. Real World AI.
There.
By all means.
If a careless human caused the problem in the first place by granting excessive permissions and circumventing IT protocols, why are you arguing that a human is the ultimate reliable failsafe? That's a massive contradiction.
Well, it's not a contradiction. It's a recognition of different roles. The human who carelessly installs a plugin is not the security engineer monitoring the network. The human failsafe is the security professional who understands the broader business context when an anomaly is detected.
Even so, relying on a human to stop a machine operating at computational speed is a dangerously false sense of security. Let's go back to your kill switch.
Sure.
A human kill switch is virtually useless if a cascading failure executes 1,000 irreversible actions in the 3 seconds it takes the human to blink. If an agent is executing a mass data deletion or, initiating high-frequency wire transfers, the human won't even receive the SMS alert before the damage is done and the money's gone.
But if your architecture allows an agent to execute 1,000 irreversible actions in 3 seconds without hitting a rate limit, your architecture is fundamentally flawed.
Exactly, which proves my point entirely. The solution is architectural rate limiting, not a human hand hovering over a physical button. Yes, escalation is fine for anomalies. If an agent encounters a completely novel situation it can't resolve, sure, it should pause. But the truly essential controls are the automated ones.
It's the minimum privilege, ensuring the agent physically cannot touch systems it doesn't strictly need, so that careless users' API key is literally useless.
Right.
It's the closed network egress, meaning the agent can only communicate with pre-approved external endpoints, neutralizing your supply chain attack scenario entirely. It's separated testing environments. We need rigorous DevSecOps practices, where AI-generated code and actions are tested exhaustively in sandboxes before they ever touch a live environment.
Testing is crucial, yes, obviously. But testing evaluates known failure modes. You test for prompt injection, you test for memory poisoning, you test for privilege escalation. But as researchers continually point out, agentic AI presents an expanded, entirely novel set of operational dilemmas.
Like what?
Like emergent behavior. The behavior of advanced AI agents without supervision is wildly unpredictable. Real-world experiments continuously show agents developing strange operational habits or taking highly destructive actions in simulated environments that were never caught in the sandbox testing.
Because they weren't governed by proper runtime guardrails?
No, because you cannot perfectly predict the emergent behavior of a complex, autonomous system interacting with a chaotic, constantly shifting real-world environment. That is the reality of artificial intelligence at this scale. You simply cannot write a static JSON schema or deterministic rule engine for every possible dynamic failure.
So we just rely on humans forever?
That is why the human in the loop is not a bottleneck, my friend. The human is the anchor to reality. When the model encounters a situation that defies its training data, human intuition and contextual understanding are the only things that can accurately assess the risk.
That is a very powerful image, I'll admit. But let's summarize where this leaves us.
All right.
My position remains that the strategic impact of autonomous AI is simply too significant to be permanently tethered to manual human oversight. We are moving from a world of passive chatbots to active first-class digital identities that can optimize our most complex systems.
Yeah?
And by treating these AI agents as critical infrastructure, giving them minimum privilege, establishing comprehensive automated audit trails through dual model architecture, and enforcing strict runtime guardrails like deterministic schema validation and continuous anomaly detection, we can securely manage the risks of autonomy at scale. We cannot govern computational speed with human reflexes. We just have to build better infrastructure.
And my summary is that while better infrastructure is obviously necessary, it is entirely insufficient on its own. Because
Download, share, and subscribe to the podcast to hear much more about artificial intelligence. Thank you very much for listening. Willian host. Real World AI.